All right, the last reaction we're going to cover in the aldehyde and ketone chapter is all about the Baeyer-Villiger oxidation. So let's take a look at the overall reaction when we're performing a Baeyer-Villiger oxidation, and then we'll take a look more closely at the mechanism. So this works on either ketones or aldehydes. I have an example ketone shown here, but I just want to write down ketone or aldehyde. And what happens is you can treat it with a reagent called a peroxy acid. So it's not a carboxylic acid. Instead, it's got this oxygen-oxygen single bond here. And this is normally more reactive than a carboxylic acid. So this is called a peroxy acid. I'll just make a note down here. And they vary depending on the identity of this R group. The most familiar peroxy acid that we've seen in this course is MCPBA. That's metachloroperoxybenzoic acid. But the reality is a wide variety of peroxy acids can be used for this reaction. All right, when you treat a peroxy acid with a ketone or an aldehyde, you can convert to something like an ester, or in some cases, a carboxylic acid. So in fact, let's even do the separate one down here. And so we'll take a look at what happens when we have an aldehyde with a peroxy acid. Instead of getting an ester, what we end up getting is a carboxylic acid. So what you may notice in each of these is that we are going to end up with a new oxygen inserted next to the CO double bond. The question is, well, how do we know which side? In the case of aldehydes, it's pretty easy to remember that anytime you do the Baeyer-Villiger oxidation with an aldehyde, you always get the insertion of the oxygen right here, meaning between where the hydrogen was attached and the carbonyl is. So you always end up with a carboxylic acid. So let's make a note there. With an ester, with a ketone, you get an ester, but it's not always clear if the oxygen is delivered on the right side or the left side. That depends a lot on the identity of the R groups that are attached. So we do need to pay attention to the R groups that are in place on our ketone. All right, so let's take a look at the mechanism in a bit more detail. And the mechanism is a bit more complicated than what we're used to, but we'll try to draw it out and be clear with it. Okay, so for the mechanism, I'm going to use a simple ketone like acetone, and I'm going to use a generic peroxy acid. And I'm going to draw my peroxy acid in a unique way, just so we can kind of see the arrow pushing a bit better. Doesn't really matter though how you draw it. And what happens is this oxygen coming off the end here will attack into the CO double bond on our ketone or aldehyde, and then kick electrons up to that oxygen. So now let's take a look at what this next intermediate will look like. And I do want to emphasize that this is under equilibrium conditions at this point. The new intermediate has oxygen with a negative charge on acetone, but now we've got this peroxy acid that was added in. And I'm going to draw my peroxy acid a little bit like this. And this oxygen over here that attacked in, because it still has a proton off of it, must have a positive charge, right? All right, so now the question is, well, what in the heck happens in the next step? Well, this carbonyl that's next door can actually grab that proton and then deprotonate that position and protonate the carbonyl. So let's see what the next intermediate looks like. It'll look pretty similar, but just proton transfer. I'm going to actually flip it so it's in the same position as it was before, just so we can keep track of things. So really all we've done is we've moved this proton here over to the carbonyl position. The original oxygen on the acetone molecule will still have a negative charge over here. So let's include all of our lone pairs just to be consistent. And we're at our intermediate. All right, so now the question is, well, what happens in the next step? It's a little bit weird, but bear with me. what's going to happen is this negative charge will clamp down. But then we run into a problem, right? If we clamp down there, we're going to violate the octet rule on this purple carbon, right? We can't violate the octet rule without causing serious problems, so we've got to figure out a workaround. And a lot of students are tempted to show this, where they kick off that group. But if we kick off that group, we're just recreating our starting material. So that's not really that helpful. So something else must get kicked off in this process. So instead of the oxygen getting kicked off, something unusual happens. This entire methyl group is going to essentially migrate over. So it's going to migrate over to this next door oxygen, that entire CH3 group, and then this bond must break. It'll clamp down there, and then this bond will kick up to that positive charge. So let's see what this product will look like. All right, so at this step, we now have the methyl group that's moved all the way over to that oxygen. So you can see we've created an ester from our original ketone. So this is our final product. But let's take a look at what's really going on over on this side. You can tell that this is essentially acting as a leaving group. That's what I've highlighted. So we've formed a new CO double bond. This top position is now a CO single bond, and we must have an R group over here. So when you look at this, this is essentially the byproduct that's kicked off in the Baeyer-Villiger oxidation reaction, and you can see that it's just a carboxylic acid byproduct. The good thing with this is it's obviously a lot more acidic than the ester we formed, so it's usually much easier to separate out from the reaction mixture. All right, so I did want to kind of go over an important step that throws people off. And that is over here, this group that I have a dashed circle around shifts over. All right, so then the question is, well, why is that group shifting and not another group? Well, in this case, we only have two groups to choose from. We have this methyl group right here, or this methyl group, so there's a tie. It doesn't really matter which one we pick. But if we had differing groups, then things all of a sudden matter. So let's make a note. Some groups like to shift a lot more than others. In fact, we can see this with experimental results, and we can tell that hydrogens like to shift really, really readily. In fact, that explains why, if we go back up, that the oxygen prefers to insert here, right? Is that hydrogen-carbon bond is a lot easier to cleave and have that hydrogen shift over. So we can see that hydrogens shift really readily, more so than carbons. And then carbons are more likely to shift if they're tertiary than secondary. So this trend seems to hold true. Then the weird thing is phenyl groups, or aromatic rings, like to shift next. And they like to shift more than a primary carbon, and a primary carbon likes to shift more than a methyl carbon. So really all of these are looking at carbon shifts, where over here this is just hydrogen. So hydrogen likes to shift really readily, but with carbon it depends on whether or not it's tertiary, secondary, a phenyl group, primary, or a methyl group. All right, so let's do a few example problems. All right, let's take a look at this situation. Let's say we've got this ketone, and I'm just going to say RCO3H. We're going to abbreviate that peroxy acid. The question I have for you is, what would this product look like? I'll just make it worth 4 points. And we could say, well, the oxygen insert here, or will the oxygen insert over here? And so what I would do is I would look at this and I'd say, well, this carbon that we're asking to move is a methyl group, right? And then over here, if we had to move that carbon, it's definitely not a methyl group anymore. Instead, it looks to me that it must be a secondary carbon because it's a carbon that's bonded to two other carbons coming off of it, right? So if we look at this entire thing kind of sliding off, we don't pay attention to that carbon because that's ultimately what we're detaching it from. All right, so then the question is, well, which one's higher priority? Well, if we go back up to the list, we can see that secondary carbons are ahead of methyl carbons, so we should get the insertion at the red arrow position. So we can go ahead and say, well, we must get an oxygen insertion there, and then the rest of the position will be on that side. In this case, you can tell I kind of flipped this upside down just to keep my zigzag notation looking nice. All right, so some of these get a little bit trickier. Let's try another one. Let's say, well, what happens if we have this situation? And again, I'm just going to make some example problems here. Again, we would say, does the oxygen insert here? Or does the oxygen insert over here? And now what I would do is I'd say, well, this is a hydrogen, quite clearly. And then over here, like we said, this carbon is a secondary carbon. So now the question is, well, which one's more likely to shift? As we saw, the hydrogen is more likely to shift. So in this case, we could use this to make a carboxylic acid. All right, so let's take a look at a slightly harder problem. And this problem is going to kind of dig into synthesis a bit more. All right, and in this problem, we're going to start with this starting material. And my goal is to create a molecule that is a diol. So we're attempting to make this molecule. We're not quite sure how, but the question is, how can we get this ring system to break open? Well, the reality is, if it's a ketone, we can't, right? If I were to add a Grignard reagent to this starting material, we would just make an alcohol, right? We wouldn't ring open it. If I reduced it, I would make an alcohol, so that wouldn't do much. If I reacted it with a nitrogen nucleophile, yeah, I could make an imine or an enamine, but that won't ring open it either. Here's the cool trick that we have with this. Is let's do this Baeyer-Villiger oxidation. So I'll do RCO3H. And as you can imagine, it doesn't really matter if we put the oxygen where that red arrow is or the green arrow because it's a symmetric molecule. So I'm just going to pick one side since it doesn't matter. And if we end up doing that, you'll notice that the ring got one size bigger. So we've got 1, 2, 3, 4, 5 carbons in the ring. At this step, we should still have 5 carbons. We've just added an extra atom in the ring, which in this case is going to be the oxygen. All right, so that's pretty straightforward, although a lot of students forget to do that ring expansion. Now the question is, well, how can we get from here to our final product? Well, it looks to me like we're reducing an ester. So if we want to reduce this ester over here, we would need to react this with LAH in excess. That would be step 1. And then step 2 would be to quench it with water, right? So what I have circled in green over here, this carbonyl, that would eventually become one of the alcohols, right? And then over here, the group that was kicked off must become the other alcohol. And in this case, it makes sense, right? We've got 1, 2, 3, 4, 5 carbons between those two alcohols. Let's double check. Got 1, 2, 3, 4, 5. So that's kind of neat that we can do that. Additionally, we could react this if we wanted to. Let's just do this for fun. What if we treated this with methyl magnesium bromide in excess, followed by water? Well, if you recall from the chapter where we talked about Grignard reagents, Grignard reagents will add in uncontrollably to an ester. So what you'll end up getting is a molecule that looks more like this, where you would have two of these methyl groups that were added in. So these two methyl groups added in from that Grignard reagent. And then the other position will be kicked off as an alcohol. So you would actually be able to ring open it with the Grignard reagent as well. But as we can tell in our final product, we didn't want to gain any carbons here, so it's unlikely that we would need to use a Grignard reagent to ring open an ester. However, if we want to ring open an ester and add carbons, then we can use that Grignard reagent. All right, this is a really versatile intermediate that I have shown over here because it can be ring opened. It's formally called a lactone, and it's a versatile precursor in a lot of organic syntheses. All right, so that's where we're going to stop. After this, we're going to take a pause from lecture material. We'll do a take-home exam, and then when we come back, we'll jump into new course material. All right, good luck studying.